Hello everybody. This lesson is going to have us simply review some of the notes and processes that we've already talked about in 7.3. As I've graded your homework, I've found some very interesting and unique ways to come up with the answers that I have on the answer key, but the processes don't really follow these rules. I wanted to review them to make sure we all are clear on this kind of step process. For sine, cosine, and tangent, you have to take the inverse on your calculator or use the unit circle to get an answer. If you are using your calculator, we have rules to get the second possible solution for sine, cosine, and tangent. Remember the rule for sine. Once you take the inverse for one angle, you do 180 minus that angle to get the second angle. Or in radians, it's just pi minus that angle. For cosine, same idea, but where cosine's positive and negative is different on the unit circle or in the four quadrants. Therefore, we do 360 minus whatever our first answer was, or 2 pi. And then for tangent, you would do 180 plus. Now, for tangent, the order in which you write that out doesn't really matter because it's addition. But for sine and cosine, order does matter because of the subtraction. And then if your answer is negative, remember we add 360 or 2 pi to that answer to make that answer coterminal. So that's just a quick review of our rules, but let's put them in action so that you guys can see what we're looking for. I've seen a lot of students just make negative answers on their calculator magically become positive, and that's not the process we want to get ourselves into. In examples A and B, it says solve for values between 0 to 360. This would indicate then that we are in degree mode. So make sure your calculator is in that mode. And it says give approximate solutions to the nearest tenth. All degrees will be using that rounding rule. Example A, 4 times cosecant squared theta equals 5. This is a quadratic example where we have just the quadratic term, not the linear term. This would be a case where we'd want to isolate that trig term, which means we'll divide both sides by 4. And we get cosecant squared equals 5/4. If we square root each side to get cosecant by itself, remember on the right we'd get plus or minus, and we have the square root of 5/4. Now if we think about that, that's the square root of 5 over the square root of 4. Now I've seen a lot of you rationalize the denominator with the square root of 4, and in theory that's a possible step to go through, but the square root of 4 is a perfect square. It's automatically 2. And if you recognize that, notice you don't have to rationalize the denominator. But because we have cosecant, what we need to do is take its reciprocal. And the reciprocal of cosecant is sine. And sine's user-friendly on our calculator. If we keep plus or minus and take the reciprocal of our fraction, now we do have to rationalize the denominator because the radical 5 is on the bottom. If we multiply by radical 5 over itself, we would get plus or minus 2 radical 5 over 5. Now, to get sine, we'll set it equal to both the positive and the negative. Like so. I'm going to give myself a little bit more room here. Oh boy, not a lot of room. Let's see what we can do with this. Okay. Take the inverse, and remember to be in degree mode on your calculator. And make sure that 2 radical 5 over 5 stays in the parenthesis. To take the inverse, once we enter this in, you should get a decimal value of approximately, let's see, where am I at on this one? Approximately 63.4, I think. And that's a positive answer in quadrant 1. To get the other counterpart for this solution, we subtract it from 180. No, not 180. We subtract the angle from 180. 180 minus 63.4 would be approximately 116.6. Now, that first angle is in quadrant 1, and the second angle ends up in quadrant 2. That's when sine would be positive, because that's the y-coordinate. For the other answer, if we take sine inverse of negative 2 radical 5 over 5, sine is negative down in quadrants 3 and 4. That's where our two answers should put us. When we type this into our calculator, we actually get the same number, but negative. We get negative 63.4. Now what we'll do to make that one coterminal is we'll add 360 to it. Negative 63.4 plus 360 would be 296.6. And that's all we do with that. We don't do anything else with that 296.6. We take that negative 63.4 and we apply sine's definition. Negative 180 minus negative 63.4 would become 180 plus, and that would give us 243.4. And that's the process to follow. We don't want to change any signs. I've seen kids subtracting from 180, adding 360, all these really kind of random steps. This should be the process you'll want to follow, and it will work every time. Let's try the next example. Example B. 2 times tangent squared theta plus tan theta minus 3 equals 0. Now what I'm going to do is just kind of move this over so I have a little bit more space if I need it. All right, let's carry on. When we have a squared term and a linear term, let's go ahead and just write it in terms of x. Our tangent squared term can be like our x squared term. And then plane tangent is like plane x. Now solving this quadratic is usually a little bit more manageable. With that 2 out in front, we do have to do the a times c rule, and 2 times negative 3 would be negative 6. Now we need to break down two numbers that multiply to get negative 6, but add to get 1 for that plus 1x in between. If we do positive 3 times negative 2, that would give us positive 1. To split the 3 terms in that quadratic to 4 terms, we're going to keep the 2x squared, and then I'm going to put minus 2x right next to it, plus 3x. That's where those two numbers come in. Together they would add to get positive 1x up above, and then I'm going to drop down the minus 3. We split the 3 terms into 4. From here, go ahead and group the first 2 and the last 2 terms. In that first parenthesis, we have 2x squared minus 2x. We can factor both a 2 and an x out of both of those terms. And that would leave us with x minus 1. If we do the same thing with 3x minus 3, factor out something they both have in common, we can only take out a 3. However, we're left with x minus 1, and that shows that it's a matching factor set. X minus 1 is one factored answer, or one factored form, and then 2x plus 3 is the other factored form. To solve for x, just set both parentheses equal to 0. In that first equation, x would equal positive 1. In that second equation, x would equal negative 3/2. It would be great if this was all we had to do, but now we've got to go back to our trig term. We were actually dealing with tangent. Because of that, we now have to set tan theta equal to 1 and tan theta equal to negative 3/2. Well, 1 looks familiar to me for tangent. That's actually on the unit circle. If we want to find tan inverse of 1, where on the unit circle are the coordinates the exact same so that they would cancel out to equal 1? We're in degree mode. In quadrant 1, we would be at 45 degrees. And then down in quadrant 3, we would be at 225 degrees. Those would be our exact answers. However, for negative 3/2, that's not one of our specific unit circle locations. This one we'll enter in on our calculator. Again, be in degree mode. We'll switch to radians in just a moment. If we take tan inverse of negative 3/2, we should get negative 56.3 degrees. And the first thing you want to do, just make that coterminal. We'll add 360 to it. Negative 56.3 plus 360 would put us at about 303.7 degrees. There's one answer. And then tangent's rule, to get the second answer, we add it to 180. But if our answer was negative, technically we subtract. 180 minus 56.3 would be 123.7. And those would be your answers in terms of degrees. When dealing with radians, it's the same process. Just remember to put your calculator in radian mode and recognize that you'll round to the nearest hundredth. So in radian mode, we're rounding to the nearest hundredth. For this first example, this is actually from your worksheet from 7.3 day 2. Cosine squared theta minus 2 cosine theta minus 1 equals 0. Again, we have a quadratic and a linear term. That means we're going to rewrite them in terms of x. This would be x squared minus 2x minus 1. If we try to factor this, there aren't two numbers that multiply to get negative 1 and add to get negative 2 at the same time. So this one does not factor. And I know in the notes I said I didn't think I would give you any that needed quadratic formula. Sadly, this one does. So we need to do quadratic formula here. Just because it's not factorable doesn't mean we can't solve it. We just have to use a different method. If we do quadratic formula, we need a, b, and c. A is the number in front of x squared, which would just be 1. B is the number in front of plane x. That's a b. Oh golly, that should be a b. There we go. And then c is the constant. Quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This simplifies. We have a double negative 2 plus or minus. On the inside, negative 2 squared is 4, and then 4 times 1 times negative 1 is negative 4. So it becomes 4 minus negative 4, which then changes to positive. And that gives you 2 plus or minus the square root of 8. The square root of 8 breaks down into 4 times 2, and then that would become, that's not where I wanted that equal sign. Sorry, I want the equal sign after that. So if that breaks down into 4 times 2, the 4 comes out as a perfect square. 2 plus or minus 2 radical 2 over 2. All those outside 2's cancel, leaving you with 1 plus or minus radical 2. I'm already going to give myself a little bit more room here. I don't think I need too much more, but I just want to make sure I have enough space. This is what x would equal. But again, we're not solving for x. We want to solve for cosine theta. If we now set cosine theta equal to 1 plus the square root of 2, and then cosine theta equal to 1 minus the square root of 2. To get theta by itself, we take the inverse. Make sure to put 1 plus the square root of 2 in parentheses. And when you do that, what ends up happening is that parenthesis is greater than positive 1. And on the unit circle, cosine doesn't go any further to the right than 1. Therefore, when we take the inverse, we get an error on our calculator. This part of our solution is not possible. Let's try the other one and see what happens. If we take cosine inverse of 1 minus the square root of 2, that parenthesis is now less than, or between negative 1 and positive 1. So that one actually lies on the unit circle. In radians, if we take cosine inverse of 1 minus radical 2, we get approximately 1.99. That's one example, or one answer for cosine. The rule for cosine's second answer, we take 2 pi minus 1.99, and that second answer is 4.29. Now, if you guys can remember all these rules, you should be in great shape. Whoa, all right, for our final example, I know we're getting kind of long-winded here. We have 4 sine squared theta plus 18 sine theta minus 10 equals 0. So what I did was I just kind of went through not the complete the square, wow. I went through the process of doing a times c split to get b with 4x squared plus 18x minus 10. And I ended up getting all the way down to sine theta equals 1/2 and sine theta equals -5. And I chose this final example because sine theta 1/2 is on the unit circle. So make sure that you're recognizing those types of solutions. Theta equals, or sine equals 1/2 on the right at pi over 6 in quadrant 1, and on the left at 5 pi over 6. And if we try to take sine inverse of -5 is way too small. Sine's lowest output value is only -1. So if you try to type this in on your calculator, that's not possible. Therefore, the only answers are the two in orange on the left. Now, your homework for today, I just want you all to log back into your prior worksheets for 7.3 day 1 and day 2. You should have a comment from me if there's a question you missed. All you need to do today is make any corrections on those homework assignments, resubmit them, and you can get a 4 out of 4 score. Tomorrow, we're going to tackle values for sine, cosine, and tangent when there's a number in front of the theta symbol. That's going to be quite an adventure.